Hey there. Have you ever looked at a graph, maybe a company's stock price or something, and just wondered, how do we find that exact highest point? Not just by looking, but for real. Well, today, we're going to dive into a surprisingly simple calculus trick that lets you pinpoint those peaks, and also the valleys, with absolute precision. Let's jump in.
So this is our mission, right? We're not going to guess. We're not going to just eyeball it and say, it looks like it's about here. Nope. We're going to find a rock-solid mathematical way to find the absolute peak of any curve. And for that matter, the very bottom of any dip, too. And to kind of get our intuition going, let's think about a roller coaster. You know that feeling? The slow climb up? That moment of suspense at the very top? And then that stomach in your throat drop. Believe it or not, everything we need to know is right there in the shape of that track.
All right, section 1. Let's start with a really simple riddle about our roller coaster. The answer to this is going to be the key to understanding what's happening at those most extreme points, the very top and the very bottom.
Just picture it. You're climbing that huge hill, and right at the very, very top, you're not going up anymore, right? But you haven't started going down yet either. For just that one split second, the track is perfectly level. It's flat. And you know what? The exact same thing happens at the bottom of a drop. This one simple idea is the key to everything.
Okay, so let's take that image and turn it into a math idea. If a line is perfectly flat, horizontal, what does that actually tell us about its slope? What's the number we use to describe total flatness? 0. That's it. A perfectly flat line has a slope of 0. It has no steepness. It isn't rising, it isn't falling. Its rate of change is just 0. This is the connection that unlocks the whole method for us.
So now we're going to take that little secret that peaks and valleys have a slope of 0, and we're going to turn it into a seriously powerful mathematical tool.
And this is the magic connection right here. In calculus, the tool we use to find the slope of a curve at any given point is called the derivative. So it's simple. If the slope at a peak or a valley is 0, that means the derivative at that exact same point has to be 0. It's a direct link.
And this gives us this beautiful, simple three-step recipe. For any function you're given, you just find its derivative, you set that thing equal to 0, and then you solve for x. That's it. The answers you get for x, those are the locations of your peaks and valleys. In math, we call them critical points.
Okay, let's put this to the test with a function we all know and love. F of x equals x squared, that classic U-shaped parabola. It turns out its derivative, its formula for the slope, is just 2x.
All right. Step 2, set that derivative to 0, so 2x equals 0. And now, step 3, solve it. What's the only value for x that makes that true? It has to be 0. And just like that, boom, we've mathematically proven that the very bottom of that U-shape is at x equals 0. See? The method works.
Now, that was easy enough for a simple function. But for those more complicated squiggly curves, we need a faster way to find the derivative. So it's time to add a really powerful shortcut to our toolkit.
This little trick is called the power rule, and trust me, it's a total lifesaver. Here's how it works. For any term, you just take the exponent, multiply it by the number out front, and then reduce the original exponent by 1. Let's see it in action. It's easier than it sounds.
So the great thing about the power rule is we can just do it piece by piece. For x cubed, the 3 comes down to the front, and the exponent becomes a 2. So we get 3x squared. For minus 3x squared, the 2 multiplies the minus 3 to get minus 6, and the exponent drops to 1, giving us minus 6x. And what about a plain old number like 5? Well, a constant never changes, right? So its slope, its derivative, is always just 0.
Now we just put the pieces back together. The derivative of the whole function is just the sum of the derivatives of its parts. So for our function, the derivative is simply 3x squared minus 6x. Okay. We've got our more complex function, and now we've got its derivative. We are officially ready to use our three-step method to find its peaks and valleys. Let's do it.
All right, here comes the most important part of the whole process. We take that derivative we just found, 3x squared minus 6x, and we set it equal to 0. This is the equation that's going to tell us exactly where those flat spots are on our curve. So how do we solve this? Well, the easiest way is to factor it. Just look at the two terms. See how they both have a 3x in them? So if we pull that 3x out to the front, what are we left with inside the parentheses? Just x minus 2. And this new version is way easier to solve.
Now think about it. If you're multiplying two things together and the answer is 0, one of those things has to be 0, right? So either the first part, 3x equals 0, which means x must be 0, or the second part, x minus 2 equals 0, which means x must be 2. And there you have it. Those are the two x locations of our peak and our valley.
Okay, so we know where the flat spots are, but we still need to know how high or how low they are. To find the full coordinates, we have to take these x values and plug them back into our original function, not the derivative. That's a super important step. This will tell us the actual height of the curve at those points.
And look what happens. When we plug in x equals 0, we get a height of 5. So one of our critical points is at 0, 5. When we plug in x equals 2, we get a height of 1. So the other one is at 2, 1. And since 5 is higher than 1, we found our peak at 0, 5 and our valley down at 2, 1.
Okay, let's take a quick look back and really lock in what we've just learned. We literally started with a simple idea about a roller coaster and turned it into a powerful tool for solving some pretty complex problems.
Honestly, this is like a new superpower. You can now take almost any function, run it through this simple process, and pinpoint the exact coordinates of its highest and lowest points. This is a huge concept in calculus, and it's used everywhere, from finding the best business strategies to designing the most efficient rocket engine. It's all about finding those optimal points.
So I'll leave you with this thought. This was never just about finding dots on a graph. It's about optimization. It's about finding the maximum profit, the minimum cost, the most efficient path. Now that you have the tool to find the absolute best point of any curve, what will you choose to optimize?